Welcome to the talk, everyone. Very glad to be with you all, even in this limited online format. I think it's very nice. Today, I will continue the next 45 minutes or so talking about POD and DMD, and we'll get into what that all means and what's it all about. Uh, I guess it's only apt to start with an overview of what I'm going to talk about today. And just so you know, I'm just going to sort of divide the talk into two portions. I'm going to talk about POD in the beginning. And I'm just going to give you a moment to ask me questions, because I know in the online format it might get lost. And a lot of the discussions in the DMD section of the presentation relies on the POD parts. So take your chances to fill in the gaps or confusions if you might have any. And at the end, we will just go over to Q&A. Just a heads up, I try to keep it a bit practical, not very abstract, so that you can actually try to employ these techniques into your own data. And hopefully it's of some value today. Well, I think it's only apt to start with a big classification overview, similar to what Kwanta presented in the beginning of his presentation. Artificial intelligence as a blanket term basically branches off into some different aspects. But if we focus on machine learning specifically, we can highlight supervised learning, unsupervised learning, and reinforcement learning as sort of three big players as it comes to machine learning. Today, we focused a lot on regression-based supervised learning algorithms with machine learning using artificial neural networks, also reinforcement learning. And just so you know, neural networks in the form of autoencoders can also be used for unsupervised learning algorithms, as Michel presented also. But the POD and DMD algorithms specifically are unsupervised learning algorithms. And they're very good in clustering of the data. So that goes with pattern recognition and order reduction. So you can build on top of what your data has a reduced order representation of your simulations or experimentations. And of course, this all feeds into dynamics and control, which I'm not entering in this talk. I just want to give you a bare bone understanding of what these techniques are and how you can apply them. And that's a whole different field and that can be highly interesting. In fact, you can combine a lot of the techniques you learned today with the POD and DMD ideas. So in that sense, I think it's very interesting. And just so you know, this is data-driven. So you might be an experimentalist working in the project. You might have numerical data. Regardless, you can apply this to your works. So you might have PIV data or CFD data. It does not matter. It's purely data-driven, and that's a good and bad thing, right? It's a double-edged sword, let's say. As good as the data is what I'm trying to say. Well, moving on, let's kick off with POD, that stands for proper orthogonal decomposition. It's also known as principal component analysis, or PCA, if you're familiar with that term. And the idea is not that new, actually. If you go back to the original formulation by John Lumley in 1967, the paper actually deals with turbulence and fluid dynamics. So this is a technique kind of born out of the field. And I'd just like to take a moment and say this is in contrast to many other techniques that are born out of image processing databases and that sort of initiative. And that's a whole different kind of conversation that is interesting to see how these techniques that were built by different use cases in mind can be applied in various fields that almost has nothing to do with the original intention, but that's not the case here. And there's a lot of variations to POD, I should note. You might have missing data that has to do with the robustness of the algorithm. You might have noisy or corrupted data. These algorithms are very good in denoising data, for example. You might have multiple data sets. You might have, let's say, hot wire measurements and PIV if you're an experimentalist, and you want to combine it into a representation of your system, of the reality. And that is possible using these techniques. And of course, multi-scale, multi-resolution approaches also, which in this context of POD has to do with spatial resolutions and pattern recognition in different spatial zoom levels, let's say. But today we're going to talk about the basic bare-bone POD and how it's implemented, how we can do it. The main idea here is decomposition, as the name suggests. And you might have a data that is a function of space and time. Let's call it y here. And point is to break it up into functions of solely space and solely time. So you decouple the effect into different aspects. And of course, this is not necessarily unique decomposition. And what POD does is to make a number of assumptions to make it a unique decoupling, and also tries to derive the total sum of this function to the minimum, so to keep the m number as low as possible. So let's see how it's actually done. This is idea of data assembly. I'd like you to pay attention to this because either on PMD or on POD or DMD, you're going to have to assemble your data in a way to feed into the system. And this is how it works. You basically make a gigantic Y matrix that is comprised of all of your data set. So that in the first column of the data, you effectively have the first snapshot of your data. Let's call it T1. And you can basically put all these columns next to each other until you have your last time step M. And just so you know, this is not necessarily, let's say, scalar data, pressure data. We're just having a column of data. So let's say you have CFD and you're working with vector fields. Let's say you have 3 components of velocity. And that's also doable. You basically stack on top of each other different aspects of your data. For example, you have a U here, you might have a V, let's call it V that is a function of X1 and T1 and so forth. You put it under U, so we'd have a very tall column in your Y matrix effectively. So just keep in mind that this is not necessarily a scalar construction of the matrix. Now, what you do here is effectively a singular value decomposition is the core of POD. And the idea is that you can decompose your matrix into the 3 matrices here, U, sigma that I'm going to call S, and V. And that's in a conjugate transpose formulation so that the equality holds. And the idea of an economy SVD is that you can actually reduce the dimensions of the U and the S matrix while keeping the equality of this transformation. So you effectively truncate both U and S, and you still have an equality, and it's a much more reliable, economically efficient way of calculating this. And the way this is very interesting, actually, may be interesting to you, that in the original formulation by Lumley, it's kind of cumbersome to implement it, and it's only, I would say, after the year 2000s or so that the techniques have become more applicable, let's say, to the actual data sets. This is one of the tricks. And important is that the U matrix and the V matrix are unitary, so that if you multiply them by the conjugate transport, you would uncover the identity matrix, and the S matrix is diagonal. And in fact, it's diagonal sorted by the decreasing only specifically positive entries. And you can also further trim down this in the truncation phase. And instead of having M columns, so you have all the columns, let's say in the U and S and V, you can further truncate this to move away from an equality into an approximation, which is the main idea of reduced order modeling using POD. And if you want to pay attention to how these matrices actually look like, you have tall columns in U that corresponds to specific value on the diagonal of S that corresponds to a row on the V transpose. And the columns of U is what we call POD modes, followed by the eigenvalue of that mode associated with that mode on the diagonal of S, followed by the coefficients that is represented in the V matrix. So now that you have an idea of it, the gist of it is you have a Y matrix that you could have an equality with the U-SV transpose matrix multiplication, and you effectively can approximate it using the technique that I demonstrated. And by doing this, you're effectively minimizing a Frobenius norm, sort of an L2 norm, as you see, kind of keeping your distance to your actual data to the minimum. And like I mentioned, the U matrix contains your modes, S matrix contains the singular values associated with that mode, and the V contains the singular vector or the POD coefficients. So that's all I want to say about the basics of how this is done, without going into complications, sort of keeping at a surface and how you can apply POD to your own data. Now let's make it a bit more practical. Let's say we want to use POD to see what it can do for us. And to do this, I'm sort of putting together a very simple synthetic signal. Let's say I have two Gaussian distributions, S1 and 2. So these are the bell curves, as you know, with the three coefficients, A1, B1, C1, and then the same for S2. I'm going to associate an omega 1 and 2 with both of the signals. I'm just going to fabricate this Y signal effectively. So here I've put together, if you can see, a Jupyter notebook so that we can go through it together. And hopefully you can see this. Make it probably full screen so we can see better. Okay. Just going to run through and walk you through how this implementation is done. I think it's very more tangible if you see actually how this is done. So just going to use the simple NumPy, and I'm just going to use matplotlib for visualizations. That's all. I'm going to define my signal, x, just going from 0 to 5, and this is my time resolution. As you note, I'm much more resolute in time than space here. And that's something to think about actually with respect to your data, whether you have more dimensions in space or time. And the omegas that I'm attributing to the data set are basically 1 and 3. So kind of a slower moving omega 1 and omega 3. I'm just going to fabricate my Y signal. So if I want to visualize this, let's look at the S1, 2 and the ensemble that we're creating. Actually, I forgot to run this. Sorry, did not import my libraries. And OK, let's visualize the signal. So this is my S1, 2, and the sum, very simple, right? So the tail ends, you have sole representations of each of the signals. In the middle, you have somehow combination of the two. Now, I can visualize it in time and actually plot a time signal. Hopefully, this doesn't take long. I'm just going to do it like a fifth of the whole duration of the simulation. And what this can show me is an animation of my signal. So this is what we fabricated right now, kind of a lower frequency component located at the position 2, and a higher frequency component located at position 3. And you can also look at it as sort of a signal path, as sort of a contour view. You can see if I put time on my vertical axis, you see some activity around the location 2 and some activity around the location 3. And you might say, well, wait a minute, I know Fourier transform. How does that relate to all of this? Well, I can do it what is called also a spectral POD analysis. And that is to apply basically a Fourier transform at each time snap of my work. And I can actually visualize it with a contour plot to see where the spectral energy is located. And that can actually isolate for me very nicely the two locations with the correct frequency associated with them, right? Now, let's move on to POD. And this is just the magic line of POD. All you do is run SVD, and I'm just going to pass a false flag to the full matrix. So I'm actually running economy SVD here. And that's it. It runs very fast. Of course, my signal is not that complicated. It's not really that fast if you're applying it to your actual data. And let's look at these three outputs of these algorithms, U, S, and V. So here, I'm just going to use a SPI function to kind of see how it looks like. And you see U is using my spatial component. I was using 100 in space and 500 in time. So my U is sort of a square matrix here, followed by diagonal of S. And these are is a very wide matrix, let's say, because I'm much more resolute in time than space. Now, we can also look at the components of the S matrix. Remember, we just had two modes that we made our signal off of. And if you look at the S matrix, actually, it can uncover for you two energy contents that sit above the rest. That is kind of telling me that only using two modes of this system, you could represent your system. You didn't have to go all the way. And if you look at the two modes, that actually is associated with the first two columns of the U matrix and the first two rows of the V matrix. So we can actually look at that. We can look at the let's say, the first column of U and the second. If I visualize that, and this is the surprising thing, I think, this is how it can decouple my original data set. So the mode 1 and 2 do not actually resemble the original data that I had, but in fact, this is how POD decoupled it. And if you remember, in the Frobenius sort of L2 norm analysis, what it's actually doing is sorting the modes by the amount of energy that they're carrying in my system. So effectively, it could only tell me that mode 1 looks like that, and that is the majority of the energy being carried in your signal, followed by mode 2. That's, I think, very interesting to visualize it in this way. And I can also look at the coefficients, or basically the two rows of the V matrix, if I present it here. So these are, I was basically making my data using purely sinusoidal sort of functions, but what you see here is actually not necessarily a purely sinusoidal coefficient for it. And that's the idea, that it differs from Fourier transform in that it prioritizes the energy content in your working data than anything else. And next, I just wanted to show what DMD does compared to POD, but that's, I think, we can come back to it afterwards. Going back to the presentation, that was sort of a demo on a synthetic signal, but if I move along into how you can apply it to actual CFD data, for example, here I'm showing some largely simulations of the UT burner. If you remember, in one of our earlier meetings, I kind of gave a presentation on how we went about designing this burner. This is some data obtained from ANSYS CFX on this burner. And of course, CFD is kind of rich. You have a lot of perspective that you can focus on. And the idea is these unsupervised learning algorithms can actually help you look into this data and decipher it, sort of. You can see on the left the velocity contours as the flow is sort of coming outside of the burner. It also is a swirl burner, so it's kind of rotating and coming up. In the Q criterion, you can see the vortex breakdown region. You might look at the flame front as a representation of the OH mass fractions. But let's apply POD to one of them. And all I'm going to do is to pick exactly the data you see on the left, the velocity contours, and it's just a cut through the plane. And I'm just going to apply POD to it to see what I can uncover. First is the most dominant mode that you can extract from POD. And this is actually the time average data that you can have in your simulation. So this is effectively the time average data in the LES that I just demonstrated. So pressure shows some activity where the burner was located. And the OH radicals basically show me where the flame is sitting. You can see the two branches of the flame in this cut in 3D space. And the swirl is actually kind of demonstrating to you the nature of the swirl burner, that you have a rotating flow as it's coming out. And I did not have to make any assumptions about my data. Just the pure data can tell you where the action is happening effectively. But I can also demonstrate the other modes. These were the first modes, so they're the mean values. Interesting technique is to somehow subtract the mean from each of the snapshots that you have. And then you look at the difference of each of your data instances with respect to the mean of the data. If you do that, what you get out of this analysis is this. So it is interesting to try to think together to figure out what this is telling me about my data. The mode 1 is sort of showing you the work that the flow is doing by pushing out the flow, sort of the pressure gradient inside of the chamber, followed by, let's say, a sort of monopole, followed by more dipoles and so forth, that will combine with the coefficient values. So I'm basically showing the U matrix columns on the top, and I'm showing the V matrix rows associated with them on the bottom. And you see that each of the modes is associated with a very different coefficient value. And it might be interesting to actually do some spectral analysis on the mode coefficients that I've done here for you. And you can see that it can highlight what frequency content the modes are represented at most compared to others. It might be interesting to you that I don't know if you're familiar or not, in the burners that we're discussing, we have this precessing vortex core. So effectively in the very center, and that center of the burner, you don't have stationary flow, you actually have a bending of that line. And it kind of spins around in what is known as the PVC. And what we can uncover here is the PVC frequency very neatly. We know it to be around above 800 hertz. And in the mode 4 already, in one of the more energetic modes, it can identify that for me. And I didn't have to do sort of introspective analysis to see what frequencies is more represented in my data. And I can also look at the S matrix here, sort of the energy content in my domain. omitting the mean value. That would be a very dominant mode if I had to look at that. But you can already see that I have a very steep descent in energy content of these modes. And that I could choose to represent my system using a number of these modes. And this is sort of a very key concept in POD analysis, that you could choose to represent your system using fewer modes than original that is available in your data. So POD is telling me you have a lot of modes. I'm just showing you here the first 20. And I might show a steep descent until, let's say, mode 10, and the rest is not that big of a deal to me. So I can choose to represent my system right until then. So this is also a sort of a knob you can tune here. If you want a lower order representation of your system, how many of those modes are actually interesting to you? And that's a discussion that we can get into in what you can actually do more with these modes and how can it relate to your fluid dynamics analysis. Actually, that was the part on POD, let's say. I hope you kind of understand the gist of it. I think it gets much more interesting when we move on to the rest of this talk, that is the DMD discussion. But just in case someone has some burning questions, something that you really were lost on, or you're confused about why we're doing all of this, it might be good to raise a voice right now.
Hey, yeah, thanks for your presentation. I was just wondering, the method, it seems very similar to, for instance, Galerkin projections.
Yes, exactly.
Although I guess, like in if you compare this method, do you think maybe it optimizes the basis functions you're using?
Yes, that is a good assessment. In the Galerkin POD, let's say GAPI POD or Galerkin-based approach to POD, you sort of discard the S matrix and the V matrix. All you do is focus on the U matrix and the modes, right?
Okay, yeah.
And you sort of go about deciphering the rest of the coefficients in a different sort of manner. What it provides you that context is only the modes. Yes, it can be directly used in the Galerkin sort of representation of your data, and that is only the modes sorted, let's say, by energy content. That's the best way to think about it, I guess.
Yeah. All right, okay. Thanks.
All right, not really sure if it's meaningful to make a long pause here or not, but I hope you're all with me. I'm just gonna go on with the rest of the talk. And next, we're gonna move on to DMD, dynamic mode decomposition. This is a sort of a difficult concept to wrap your head around if it's the first time you're coming around these unsupervised techniques, I would say. But the gist of it is you kind of combine POD with discrete Fourier transforms. So you kind of make use of the data you have available to you when it comes to the time coefficients to sort of make a better judgment of what is the modes in my system, or what should I actually look like, the more important, more relevant modes in my system. So POD might, like you saw before in the pictures, might show you a lot of modes, and it's hard to figure out exactly what that means. If you look at the DMD modes, it's a far more useful practice to try to decipher what they actually mean, because they're somehow more informed by the physics of your data, let's say. It's a more physical-based approach in deciphering the modes of your system, let's say. And it's a relatively newer technique. It's developed by Peter Schmidt in 2010. And it is, again, another technique, surprisingly, coming out of the fluid dynamics field originally. And it's important to note that there's some fundamental differences to POD. And I'm going to go about describing to you guys how you can actually implement DMD to your data sets. And just so you know, these are data-driven algorithms, so you can just, similar to what Michelle was saying, implement a lot of these algorithms, not really that difficult. You just have data, you can just plug it in and see if it's valuable to you or not. So here in this talk, I'm just focusing on how I can apply this to my data set sort of question. That's the main question I'm trying to answer here. And there's a lot of extensions with DMD as well. You have GPU CUDA accelerations. In my experience with it, you can have significant data improvement, speed improvements to your data. But of course, as it is with the GPUs, data coalescence can be almost to the point of counterintuitism, sort of detrimental to the speed gains that you might have. Compressed sensing is another idea. What it does is basically you have your domain and you do not have a full representation of all of it. What percentage of all of this domain data I need to be able to accurately predict the modes of my system? I might have hot wire measurements, for example. These are like, let's say, sparse measurements in your data field, how it can relate to constructing modes off of that. Or might have noisy data. This is actually done very impressively in terms of image denoising or refocusing even. And when it comes to multi-resolution, in this context, we're talking about temporal resolution. So if you zoom in time, what sort of patterns you can discover in that resolution versus a larger one. And also robustness, you might have missing data, et cetera. So if your specific problem has any of these initiatives in it, feel free to look further into this. There's extensive work being done as we speak on how you can improve this to make it more suitable to a lot of data sets. And you cannot speak about DMD without bringing up the Koopman analysis. It's recently mentioned to me that Koopman is actually a Dutchman, so I should not say Koopman, I guess. But the idea is not that new. It goes back to 1931. And the idea is sort of trying to say, how can I linearize a system in a very basic term? Now, let's focus on a system with the state vector x. You have an x represented at time snapshot n, and you're looking at the evolution of that xn, and we're going to call it xn plus 1. And the idea is that this xn plus 1 is a function of the xn, is a nonlinear function that can evolve xn into the future. In the same sense, xn plus 2 is the function of xn plus 1, and so on and so forth. And it would be absolutely wonderful if this f was a linear function. Then we could apply all we know about linear control. The whole rich knowledge of linear control would be applicable to our system. And Koopman analysis ties in very well with this, because in the Koopman analysis, you look at an observable, or a g of x, so a function of this state vector. And if you look at the evolution of your data from the perspective of that function, there is a Koopman operator k that can be identified as a linear operator that can evolve your system into the future, right? So the trick here is like, what is G? And if I could find G, then I would have a linear system in turn, right? And the Koopman operator, in the formal sense of what it actually is doing, is turning a finite nonlinear dynamical system, which was the F, and it was finite in space. You just had one state vector that was being projected into the next. And it takes it into an infinite dimensional system of function space that is linear. And if I lost you right there, I'll try to bring it all back together right in the next slide, where I go about a bit more practical and how we can actually do this. And the idea is the same always. And the DMD is trying to kind of giving you a best linear approximation you can possibly have to your dynamical system. And it does this by approximating this infinite dimensional Koopman operator. Right, so I hope you sort of understand the gist of what we're trying to do here. And I have to bring it back to the idea of data assembly that we had in the beginning again. Remember, you had this Y matrix, sort of putting all your data in the columns going on to the end. Could be a very gigantic matrix. Imagine you might have CFD of very fine resolution mesh, and this translates to a very, very big Y matrix. And sort of what I do is to take the Y matrix and sort of shift in time each column into the next. And I'm going to rename my Y matrix into what you see here on this slide. It's going to omit the very last column of my data. So here I'm having Y that goes from columns of snapshot 1, 2, until 1 before the end. I'm going to make a Y prime matrix that it starts at the second snapshot and goes all the way to the end. And you might see what we're doing here. We're basically trying to see how each Y is evolving into its own next snapshot as it relates to my whole data set. And as sort of a locally linear approximation, the Y prime is almost a linear function of Y, let's say. And the whole idea is to try to find this A here, right? You might look at the bottom formula here and say, well, if I want A, I just have to have a Y prime, and I multiply it by the inverse of Y from right. And you would not be wrong. You can have a Y dagger, the Penrose inverse, pseudo inverse of your matrix, and that will be it. But just so we know, this is again minimizing the Frobenius norm like before. And the main problem is converting that inverse is not a good idea. You never actually want to compute the inverse of such a big matrix. Might just be impossible to do. And the idea of DMD is to leverage the basis of POD. If you recall from SVD before, Y was equaling US V transpose. So I just want to substitute that into my A. That's what you get. You get a Y prime multiplied by the inverse of Y, and of course the matrix multiplication, so the order is reversed. And now we have this A matrix represented in this new way. What we do is project A into its POD modes, U. And by doing that, basically computing the multiplication U conjugate transpose A U, I would construct what I know as A tilde here. I was going to name it. Now you might say, why are you doing this? Why do you make A tilde? And the idea is A tilde is a much nicer function to work with, much nicer matrix to work with. We can uncover its eigenvectors and values. And it's very good for us because it has the same eigenvalues as my A matrix. And it can be shown. This is another paper, I think, by Jonathan Tao in 2014 that shows if you construct this phi matrix and you look at the eigenvectors of that, basically columns of phi, it's the same as the eigenvectors of your A matrix. So all this trickery was to figure out the eigenvalues and vectors of my matrix A without ever actually computing it. So I skipped that inversion of my matrix in that part. And this is the whole appeal of DMD that can actually kind of get you that linearity of your system, locally linear system, without ever computing the actual invert of the A matrix. So that's the main idea behind. And it's actually pretty effective. You might say, well, my system is highly nonlinear, how it can be useful to approximate it with a linear system. Well, you'll be surprised how it can well educate itself in how your system is evolving in each time step. And it's highly data sensitive. So you might have to apply it to your data to figure out if it's working out for you or not. Let's be a bit more concrete here. I'd like to also jump back quickly before I forget into here, if you remember my Jupyter notebook. And my data here is much more simple than an actual CFD data set, let's say. So all I can do is effectively get a pseudo inverse of my Y matrix. If you remember, it's just a synthetic signal, so not that big of a deal. And I construct that A matrix basically directly. And if I do that and I try to show you, it can, of course, uncover my original modes to the exact same shape and location that I expect it to be. And this is kind of a difference in POD that does it in a fundamentally different nature compared to DMD. And if I kind of bring it back to my slides here, how you go about and implementing it in MATLAB, let's say. So, well, it's just a very straightforward, stepwise algorithm. Let's say you have your data, you just prepare your Y and Y prime matrix, run economy SVD on your data sets. So that's your U, S, and V matrix. Just gonna pass an econ flag to keep it basically the unnecessarily larger matrices can be trimmed down without the loss of data. You compute your A tilde, as we discussed before, and you look at its eigenvalues and functions, vectors, sorry, W and D. And then from this discrete time, you sort of construct a continuous time frame, omega, by using the D value that you uncovered before. And now you have your phi matrix that you can construct using W from earlier. And this would be your modes effectively for your DMD. And what you can further do is to also initiate your coefficients using the very first instance that you had. So I'm just going to use the first column of my Y and make this B coefficients. And now I have a Y DMD. I have a representation of my Y value. That is my phi matrix times its coefficients times e to the omega t to evolve it in time. Now here I could confuse you with a lot of different examples online, but what I chose to do is to go back basically to the same alias that I showed you before. And what I can do in applying this technique into a CFD data set. Well, here it is. I have my velocity field on the left. That is a full rank decomposition, so I'm not doing any reduced order modeling here on the left. And I'm just showing you my DMD reconstruction. And in fact, this is almost identical exactly to the actual data set, so I chose not to even show it in the slide. What I have in the middle is just choosing a fewer number of modes into my reconstruction. And what that is choosing about, I think, 15% of the existing modes in my system that DMD could not uncover for me gives me the middle result. So if you look at it, it's sort of a washed out view of what you have in the full system representation. And that is a reduced order modeling of it. Might be interesting to you that in the first instance of this video, so if I go back to the very beginning and I pause it there, you have exact same representations in the middle and left because I initiated my data exactly in the same moment of time. But as the system evolves, you see that a lot of dimensionality of what you see in the left is lost in the middle because it's a lower order representation after all. And of course, if my system had very few modes, let's say only 100, I could reduce this dimensionality also and not miss any data. And the fact that I am missing data means that my system is actually very highly dimensional. And interesting part of this might be what you see on the right, the prediction part. And you remember I have modes and I have time coefficients for these modes as well. Now I can use these time coefficients to evolve my system, starting the initial point, as you saw, initialized with my original data set. And I kind of went forward in time using my operator. What happens if I go beyond the dead point, the end point of my data? Well, that's what I get in the right. So that data is purely newly generated using DMD here. It's just taking all the dynamics that it learned from my simulation, let's say, and it's evolving it through time to see how it behaves if you push it past its last snapshot. You could be doing this with experimental data or CFD data. And in a very periodic data set, let's say you have a very purely periodic representation of your data, this prediction would be absolutely perfect. You can run it into infinity. And the more non-periodicity your data has, the nonlinear terms also take over after a while. And this extension into the future is more limited, let's say. Yeah, and that was sort of a 40-minute presentation on what POD and DMD is. And remember, the idea here was to kind of pique your interest in what you can do with these, how you can implement this in your data sets. What I think you take away from this talk is how it can be done. And I think this is only a starting point in taking it further, what you can do with it. Niels hinted at the Galerkin projection methods. It's very interesting how you can use these modes there in that format, in that frame. But I think this is very applicable to a lot of data purely because it's unsupervised, data-driven, and yeah, you can basically apply it to any kind of data and see how nicely it behaves. And with that, I'd like to conclude the talk and looking forward to the discussions.
Thank you.
Okay. Thank you very much, Alireza.